for those of you who don't know me, my name is Ling. I'm filling in for Alec today. I'm introducing Scott Stinner. He got his bachelor's at Lafayette College. He joined Penn in 2011. He got his master's in 2013, and today he's going to be presenting his work on integrated circuits.
Thank you. So I'm going to be presenting on flexible cadmium selenide nanocrystal integrated circuits. I'm going to apologize before I begin the talk that this talk was originally intended for material scientists, so I've tried to reorient it a bit so that you have some idea what's going on. But if you're at all confused, please stop me and ask a question, and if I'm over-explaining a simple circuit concept, please just roll your eyes and I'll move on. But this work was recently published in Nanoletters with a whole slew of other people, because this was several years' worth of work combined together. So yeah, let's get right to it. So what do I want to talk about? I want to talk about some background and some motivation to this project, and what exactly we're doing and where exactly this work comes from. Some new process requirements, which were interesting for this work that we did, and then of course the actual circuits that we built and their performance. So going into the motivation is to build flexible integrated circuits. Integrated circuit being defined as multiple transistors connected at a chip level. So the motivation to this is obvious. I mean, ICs are in everything, from phones, sensors, anything like that. And flexibility makes them more robust, allows them to conform to an environment, and allows us to put them in many more places than we could before. So the use of nanocrystal technology, and specifically, is that it allows us to use novel deposition techniques like inkjet printing. That there are people working on building circuits by literally just inkjet printing on nanocrystals onto a surface, and and it creates whole functional transistors and whole integrated circuits. So the semiconducting layer that we're focusing on is one that my group developed back in 2011. It's based on cadmium selenide quantum dots with a solution state thiocyanate ligand exchange. So those are a lot of big terms that I'll explain a little bit in a moment. So basically what that means is, you have a quantum dot. And what a quantum dot is, it's a little ball of a semiconductor or a metal or something like that, typically about 5 to 10 nanometers in diameter. And when you synthesize them, when you make them, you put these big, long, insulating ligands on the outside of them. And so when you assemble them into a film, as you can imagine, there's very little charge transport. There's very little electrons that can actually get between these particles. There's a whole lot of space and everything. So what they developed back in 2011 was the ability to replace them in solution with these short, non-insulating ligands, which allows the film to be much more compact, allows these balls to essentially form a somewhat continuous film. I'm not going to go into the optics and the other properties that they've been using for solar cells and such, because I'm only focusing on device properties, but pretty much what we focus on is just trying to get them into a contiguous film that we can use as a conducting layer. So what I'm working on is building these circuits on Kapton substrates. So Kapton is, if you've ever seen it, it's a yellow plastic. It's very high melting point, very high tensile strength, and you can get it in like 25 micron thick sheets that you can work on. So previously, back in 2012, just as I was beginning my work, they finished up work that was based on shadow mask patterning, which are these physical cutout chrome masks to make the metal layers. And the problem with that is you can't make anything very small. So that picture on the right, that's about 10 square centimeters, and that only has 12 transistors on it. So as you can tell, that's not particularly useful, because that's huge. That's absolutely monstrous compared to any technology today. So the motivation of this work was to transition to a photo pattern structure, basically transitioning to something that we can build on a single micron scale, or even smaller, potentially with better equipment. But that introduces some problems, like some fabrication process changes. So increased air exposure and larger air uniformity are concerns, because these cadmium selenide nanocrystals have a very high surface area to volume ratio, which makes them very, very oxygen sensitive. So this became a solved problem in 2013 with some work that was done that I'm not going to dig into because it's far too complicated, on the effects of indium doping and the recovery effects of the indium actually kicking oxygen off of the surface of the particles and recovering these devices back to functionality. So this became a solved problem in 2013. And the next problem that we needed to solve was just the fact that there was a whole lot of chemicals involved in this process. And that introduced a whole slew of things that we'd never had to deal with before. And it made us develop a new via procedure, which I will now explain. So we really like Al2O3 as a dielectric because high dielectric constant, low leakage, and we can use an ALD, just basic chemical vapor deposition, to make it. We can just form it on any surface. We don't need to grow it. It's, we can just put it there. But the devices themselves, we really needed to use aluminum metal itself as well. And part of the reason is that the Al2O3, if you deposit it on gold, platinum, things like that, it's not particularly stable and it doesn't like to stick. So it tends to delaminate even if you do form a consistent layer, unless it's very, very thick. The other benefit of aluminum is that the work function's closer to that of CAD cell. So then we're decreasing our threshold voltages and keeping a low voltage operation, which is what we're focused on. But aluminum metal is very reactive. It's not very stable. It tends to like to form oxides very quickly, and it just isn't very nice to work with. So when we look at our structure, when we're building one of these semiconductor transistors, our gate is on the bottom, and our gate's what we actually make out of the aluminum, and our source and drain are on top of the semiconductor. So this is essentially our structure that we have to create. And the problem is that to create true integrated circuits, you have to also be able to create this structure, where you actually have a pathway through the Al2O3 that you can connect to, that you can connect on the chip from the source and drain to the gate layer. So that led to some issues, because when we want to make a hole in the Al2O3, and we pattern the photoresist, and we do a chlorine plasma and etch down through, the chlorine plasma etches the Al2O3, but also etches the aluminum, and it etches the aluminum very, very quickly. And the tool that we have in the nanofab, we can't control it well enough to be able to only etch partway through the aluminum. So we were etching away all of the aluminum, and when we tried to refill to actually make a via, we couldn't make contact. We had nothing to make contact to. So the solution to this came with many, many, many iterations, but it came with a suggestion of putting gold under the aluminum, that we can actually etch through the Al2O3, through the aluminum, but the chlorine plasma won't etch the gold. The gold's a noble metal. It'll form a thin layer on top, but it's not going to do very much to the gold. And then we can refill that with gold, and now we have a conduction path through the Al2O3 layer to the gate. So with these new processes and such, we can then create the circuits that we did. So first up was just basic single transistors. They're good performance for a solution processable material, which is a key point of this, but they're not particularly high performance in the grand scale of electronics. Like we're talking, silicon has a mobility of over 1,000 and such. So like we're not looking at really, really high frequency applications. We're more looking at low frequency applications, and with moderate performance transistors. But the threshold voltage here is key, because with a 1 volt threshold, we can operate these devices at ranges of 2 to 5 volts, which allows us to start looking at battery powered applications, and RFID tags and things like that are powered on low voltage supplies. So building from the single transistor, the next step is an inverter. Something pretty simple, just 2 transistors. So we only have N-type devices. If anyone's ever done any integrated circuit design, you'll know you love when you have N and P devices, because you can just put them together and and they're complementary and they make a nice circuit. But we only have N. So what we have to do is we have to make this saturated load design, which utilizes basically 2 separate transistors, a driver and a load. And the load, there it is this system where the drain and the gate are connected together, and this essentially produces a resistor. There's a minimum voltage to turn it on, but effectively this creates some form of a resistor that we can use to actually make this into a functional inverter. So when we constructed these, we built them. So the output voltage swing is about 80% of the power supply, which isn't great, but that's part of the limitation of the saturated load design, is that you do lose. As you can see, the low side it's pretty close to zero, but on the high side you do lose quite a bit of your voltage swing. As far as gain is concerned, we were able to design devices with gains just above 2, so right around 2 volts per volt, which is enough to really build this into an amplifier. So of course this is an inverting amplifier, and so we bias it within this region here, and it's considered the operation region. And with that biasing, we can then input a smaller signal and output an amplified signal directly from these devices. And again, it's inverting, so that's where the 180-degree phase shift of the signal comes from. So, as with any amplifier, it has bandwidth. So, the bandwidth of these devices is about 6.8, it's not 600, I wish, 6.8 kilohertz. Not particularly high, not particularly great, but one thing we did is we started calculating out a theoretical bandwidth. And we got 9.8 from our theoretical calculations. And one of the things we have to consider is that when we do these measurements, we have to do them in an air-free environment, because we really haven't reached the point that we can encapsulate these whole IC systems in another material and take them outside of the nitrogen environment. And so part of this process is we have these massive probes with long BNC cables and everything, and they add a tremendous amount of capacitance to the system. And what we're looking at is, if we do the calculation without the probe, we get somewhere around 100 kilohertz. And so single kilohertz takes us into the range that we can do sensor applications and low-frequency data processing, like RFID tags and things like that, are all plausible with a 6 kilohertz bandwidth. But 100 kilohertz bandwidth starts to push us into the range that we could do audio and telecommunications applications that really kind of open this up for some really interesting applications. Along with the amplifier, you can put more transistors in and make logic gates. So we built a NAND and a NOR gate, a NAND gate just being basically an inverter but with 2 transistors in series, and a NOR gate, the same thing except with 2 transistors in parallel, allowing us to build complex logic in the end. And we've tested their functionality by basically just taking 2 function generators, with one with half the frequency of the other, and inputting them into the inputs of a NAND and a NOR gate, and we saw very consistent performance, that there's no drastic shift between different input combinations or anything else. It's very stable output, which shows us we could actually build more complex logic. Unfortunately, on our pattern, we didn't have any more complex logic to try, but we could. And the last thing we built was a ring oscillator. So basically, a ring oscillator, it's an odd number of inverters tied together in a ring, and because an odd number of inversions is unstable, it oscillates. The device performance and the capacitances and how large the devices are and everything else determines the oscillating frequency. And one of the keys is that this displays the ability to create large area uniformity, because essentially for this I have to get 12 transistors to work in parallel, which is something that's sometimes quite difficult with these novel materials. And if you counted there, you'll notice there was a 6-stage. There's a 6-stage used to buffer the output of that heavy probe load on the system, because if we just put that down there, it would drastically change our performance. So one of the keys to a ring oscillator is noise margin. And noise margin is basically defined as the ability of one device to switch another device. And it's measured with what you'd call an I diagram, which is a transfer curve overlaid with its inverse. And basically this is just the transfer curve here, and then its inverse is this. It just flipped the x and y axes to basically get what the next device is outputting, in essence. And it's highlighted. It's always usually highlighted with these little boxes, which is why it's called an eye diagram, because it looks like a little creepy face staring at you. But all of our devices are displaying a finite and reasonable amount of noise margin, which is a good sign. And this is displayed in a ring oscillator. And so for a ring oscillator, there's a characterization factor called the delay per stage, which is how it allows us to compare ring oscillators from all different types of materials, all different designs and everything to each other. And it's basically the amount of time for one device to switch to the next device. So it's a single device measure, is in essence. And it eliminates, the biggest variation is the number of stages in your ring oscillator. So ours uses 5. I've seen them all the way up to 31, as few as 3. Everybody picks their own number and just kind of goes with it. And it's a pretty simple calculation. It's just 1/2 times the number of stages times your measured oscillating frequency of your ring oscillator. So for our systems, at a 2-volt input, we got a 13 kilohertz oscillation, which is a 7.7 microsecond delay per stage. And at 5 volts, we got 65 kilohertz oscillation, which we were really surprised about, and a 1.5 microsecond delay per stage. We were disappointed we didn't quite get into the nanosecond range, but so close. And that brings up, like, what is a comparison with other technologies? So this is focusing on solution processable materials only, because that's where, that's the area where we really want to focus on this technology becoming viable. And on the filled symbols are rigid substrates, and the open symbols are flexible substrates. So, this includes carbon nanotubes, organics. This nanocrystal spot was the previous work that I mentioned earlier with the shadow masks. Again, very, very slow, because you want to push down into this corner as much as you can is basically the goal on this plot. And the devices that we built fit right in there, which, there's some metal oxides that are, sol-gel metal oxides that are doing a bit better, but they have to be on rigid substrates because they need annealing temperatures in upwards of 500 C to make some of these metal oxides. So that's why those are all on rigid, but these are our flexible substrate devices fitting in there right where we wanted them to. So where are we going? What's the eventual goal? So one of the issues overall with this technology is that the nanocrystals, they require this fine-tuned exchange, and we can only make them in small batches. Like when I do a deposition on a 4-inch wafer, I make 400 microliters of solution. And for a commercial process, that's laughable. So what we're working on right now is a more reliable process that we can scale up to actually make this somewhat commercially viable and not just a cool science experiment. The other portion that I'm working on is integrating this into sensor networks. There's a lot of money in bio right now, so I'm getting a lot of money from the med school to integrate these with brain sensors and other surface sensors that I can build something that can literally lay on your arm and wrap around your arm, but and puts an amplifier right at the site of the contact, so that you have an amplified signal coming right out of the site of your sensor network. And that's what I had. Does anybody have any questions?
I do have a question on the minimal feature size you have currently, and if you push further down, what would the obstacle be?
So, the minimum feature size on these was 5 microns, and that's limited by the contact photolithography we're using right now. Anything smaller than that, we've had resolution issues as far as blurred contacts and such. So, smallest feature size we'd been able to make so far was 5 microns. What I would say the most difficult part of this would be is actually doping. One thing I didn't really go into in this presentation was the doping of the materials, because it's very difficult to control the doping, because if I put too much dopant in it, they just become metal. They overdope very, very easily. And so what I would say what the most difficult part of actually scaling this down even further would be finding a different way of doping the material.
And you didn't choose EBL just because of the throughput, or what?
Yeah. We were trying to make large circuits. When we actually, we at one point tried to draw out the ring oscillator and discovered it was going to take like 26 hours to draw by EBL, and it just, I can't I can't afford that kind of time.
I guess now that you can also
yeah.
It's too small an area, you probably cannot
Yeah.
make large.
So that was one of the focuses of this, was to actually make it that our final product was a full 4-inch wafer size, and we had basically I think it was 92% yield across the full 4-inch wafer.
And I'm just curious, how would you you just have your Kapton tape on top of a carrier 4-inch wafer and then spin a photoresist, or how
Pretty much, yeah. We had a carrier wafer. We used gel pack on top of a carrier wafer, and just put it on, and then we just peel it off and put it on the hot plate to anneal it. And we never. So someone at one point did tests to figure out the maximum metal thickness that you could put on before, when you were like peeling it off, it would start to crack, and it was something like 200 to 300 nanometers. And we're working, like our metal layers are 20 to 30 nanometers, so we're well below those limits, and we've never seen any effects of breaking of the metal layers when we've peeled it off or anything like that. Brock's giving me an odd look. Any other questions?
Could you go back to two slides, like 30?
Slide 30. Sure.
Question. Yeah. So, you want to push down into the lower left quadrant of this thing. So I guess this is you want lower voltage devices, and you want them to operate faster.
Yes.
Is that the right interpretation?
Yes.
Okay. So what what's the limiting? What are the limiting factors that keep you away from that?
Well, one of them is threshold voltage. So these devices had a threshold voltage of around 1 volt. That's one of the biggest limiting factors of all this, is threshold voltage. And you can squeeze your threshold voltage down by making your oxide layer thinner and thinner and thinner. But we're already working at like a 15 to 20 nanometer oxide and seeing some leakage. So that's one of the biggest difficulties in this, is just thickness of the oxide, because in a lot of these processes, not everything is completely smooth. So you have to keep your oxide reasonably thick to keep it from leaking and still being able to form over all the features.
Okay.
The cadmium selenide, is it still toxic as a nanodox? Toxicity biologically-wise?
I think so. We've done experiments where if we encapsulate it in parylene, the whole structure, just put the whole thing in the parylene coater and encapsulate it in parylene. We've soaked it in saline solution for days and haven't seen any seepage or anything like that. So those are kind of the experiments that we're falling back on to say these are biocompatible. Yes. So we can coat it with polymers basically and seal it.
Can you talk a bit more again on the deposition of CdSe structure?
I don't have any slides on that. So it's basically what I do is it's a chemical reaction process that I do. That I basically strip off those long ligands, put on the short ligands, and then I get a dispersion which is stable for about 10 minutes of nanocrystals in solution. And I just...
Stable means non-agglomerated?
Yeah, so it's not... So But after about 10 or 15 minutes, they do start to, yeah, blanking on the word, but you know what I mean. They start to aggregate. That's what we're looking for. So, you know, so it's kind of like temporary stability in this solution. And then what I do is I just put that solution onto whatever I want to build the circuits on, and I spin coating. I just put it on. It's just like a spin coater, just like you'd use for photoresist or anything like that. And that's how the layer is formed.
You just mentioned you need a large amount of the how many gallons it was?
How many?
The solution of the.
Oh, 400 microliters.
Oh, micro.
It's just, the problem is if we've tried to scale up, like the procedures that we do, and even just like scaling up the ratios doesn't work. So we're working on procedures to scale it up, because right now 400 microliters isn't going to get you very far. Oh, wait, one.
What about the scaling doesn't work? What points break down?
Like which scaling? Like the length scaling or the?
When you're trying to increase the scale of just total number of things you're manufacturing, make sure that when you try and just scale up.
Oh, see, I just mean like when I'm trying to scale up the size of the solution that I'm making, it breaks down. So we typically, like our original work that was done on this developed a recipe around a 400 microliter solution, and it works. But what's difficult is, if I just take everything that I'm using and double it, it doesn't. So we don't know. I'm working with Murray Group and such to try and work on why, because that's been one of the biggest pitfalls in all of this. Is everyone looks at it and goes, okay, well that's cool. How do we do that? How do we actually make something out of this? How does it be, change from an experiment in a lab to actually producing it for an industry?